Well, I'd like to touch upon one last topic in here within the banner of computer-aided engineering and related capabilities within SolidWorks. And this has to do, and we'll do so briefly, but with a very important topic of FEM, finite element method, also known as FEA, finite element analysis. You'll hear both of those terms used effectively interchangeably. So the finite element method is a powerful numerical technique for engineering that was established rather recently, think the last few decades, and even more recently has become widely available in modern solid modelers. The finite element method is what we call a field solver. So it enables us to take a volume of material, discretize that volume into much smaller values, and solve fundamental equations, and these are all differential equations, fundamental equations at the volume level done at a very large scale. So this is over hundreds of thousands of elemental volumes sometimes, enable us to get individual readings for each one of those volumes, and therefore being able to give us an overall distribution of any particular property, being the stress in a part, the displacement under a particular loading. So that's if you're talking about structural analysis. The thermal distribution, the pressure and flow distribution, if you're talking about flow analysis. The electromagnetic qualities, so this is even transcending, the field of mechanical engineering, well into others, such as electrical engineering, acoustic properties, chemical properties, diffusion, just about anything that you can imagine in engineering. So really this has become a tremendously important branch of engineering analysis. Okay. So this capability is built into SolidWorks. There's quite a bit of math that you need to understand that underlies these tools and these techniques, at the very minimum to be able to apply them properly, even if you're not working at that level of detail. The mathematical, setting up differential equations and so forth, you do need to understand very well how the loading is being applied, how the model is being constrained, what we call boundary conditions for these differential equations, in order to make or produce results that actually make sense. Okay, so that'll come with time and with practice, but for now I just want to introduce some of these capabilities. So we'll begin with a very simple one. In fact, this is a tool that's even available at the entry-level SolidWorks. So this is one that you do not need the SolidWorks premium capability, the high-end analysis capability, although if you were to turn that on, then you would get a far wider range of options and fine-tuning that you can do to your simulations. But we'll use this as an example here to illustrate, and we're going to do here, as you see on the screen, this element of the toggle clamp. And what we're going to do here is set up a loading condition and then find out where the maximum point of stress is. Okay, now we expect, for a part like this, that the maximum stress is likely to happen, right at this corner. And in fact, we've done well in there to put in a little bit of a fillet in order to decrease the potential for stress risers. So let's go ahead and proceed with our analysis. That particular analysis is going to be found here under the Evaluate tab. Okay, so if you click under Evaluate, where we did measure and mass properties, and things of that nature, we'll also find something called Simulation Express Analysis Wizard. Okay, so this is the entry level, really very, very basic stress analysis module within SolidWorks. Okay, we'll go ahead and turn it on. Okay, it loads up, and you see that this is going to walk us through a wizard style interface here on the right. So we'll go ahead and click on options in here. Okay, so the options will give us the ability to switch units. Let's go ahead and run this particular analysis in units. Okay, it says there show annotation for maximum and minimum in the result plots. Sure, we'll say okay to that. And when we click next in here, notice that the first business in here is to specify the fixtures. It says here, apply fixtures to keep the part from moving when the loads are applied. Okay, this is what I was referring to before when I said boundary conditions. What underlies, the math that underlies all these analysis is the solution of a very large number of simultaneous differential equations that describe the physics of the problem. In this case, this is a solid mechanics relation between loading and strain of the part. Okay, so the fixtures in here refer to how we fix the part so that it's not able to move. So this is all fundamentally a static analysis. Now, in this case, what we're going to do is we're going to fix these hinge points in here. So I'm going to select them, just by clicking them, or rather, I guess I'm going to come here to add fixture in here, and make sure that I'm selecting the parts that are not going to be subject to motion. Now, there's a lot more to say about this. This is just a very simplistic, first approximation of how we're going to fix this part. So we're going to assume, even though that those are actual hinge points where the part can rotate, we're going to imagine as if we were freezing in space those particular points of the part. Okay, and then what we're going to do is apply a load at the point of contact of the toggle clamp, and that will create a static loading condition that we can then analyze for the corresponding stress distribution in the part. Okay, so we are now done adding our fixtures. So we'll click OK. It's giving us the option to edit these fixtures, but we'll go ahead and move on to the next step in the analysis, which is to apply loads. Okay, so now here you can apply it as a force or as a pressure. We'll do a force. And the phase for the force that I'm going to select is this one here. Okay, so I'm going to come select that force. That force is being applied as a normal force. In there, we can select the units. So let's go ahead and put in there some force, let's say 1,000 pounds, just to see what happens, to make it interesting. And this is a force that is distributed among that particular phase. Okay, so that's the paride. Okay, so we'll click OK. So I'm done now with the application of the force. Okay, I'll click Next. Now the next is the material. The material, I had already applied plain carbon steel, so it has several properties in there that I'm not in need to modify any further. Okay, so we'll click Next at this point, but if you didn't have the material assigned, this would be an opportunity to do so, and you can select the material from any of those available in the SolidWorks library, which is quite extensive. Okay, so we'll click Next, and frankly, we're ready to go. At this point, I'm going to say Run Simulation. Okay, so in the background here, what's happening is SolidWorks is discretizing the volume into a series of elemental volumes, and it's playing an animation here, the purpose of which is to do just a quick sanity check, make sure that we have restrained the model properly, that we have applied the forces properly, and that the deformation occurs as we would expect. Now, don't worry, this deformation is greatly amplified and exaggerated for your benefit, so that you can get a visual feedback, that everything has gone in accordance to plan. Okay, but under normal conditions, particularly if you're using proper engineering materials, hopefully you would not be seeing this type of displacement. All right, so we're good. The animation is basically just a sanity check. On the simulation, SolidWorks is asking us, does the part deform as you expected? Okay. If not, then you likely have a problem with your application of fixtures or forces. Otherwise, you can hit yes to continue. And now what we're going to do is create a plot of the so-called von Mises stresses. Okay, and again, don't worry about what that means. Just take that to mean an approximation of or an indication of where the part is likely to fail. Or you can also show the displacement. Okay, so we'll show the stress field in here and click it. And now we get what's called a heat map of the stress distribution in the part. Okay, so you can see that the cool colors in here, the blue is where the part is not being stressed, and then we get all the way to the red here, which is where the part is experiencing the stresses. Okay, you can see here that the maximum and minimum point of stress have been identified for us, so we can take these labels out. And we can see that there's a stress and they're happening. So if we look underneath, sure enough, the maximum stress is happening right where we expected. Okay. Okay, now we can also express this in terms of the so-called factor of safety. So this is going to be a number that expresses how far above the experienced stress is the capability of the material to withstand that stress. Okay? So if you have a stress of, say, 1, but your material can take 5, then you have a factor of safety of 5. That's just the ratio there. So let's see. Let's go ahead and check the factor of safety. Here, this is, the way you want to plot this is anywhere where the factor of safety is below a certain number. Okay, so in this case, we can see that we are encountering a situation where the factor of safety is actually 0.8. So let's go ahead and find it. And sure enough, this tells us that under an application of 1,000 pounds, which was of course quite high, for this clamp, we are in fact going to exceed the allowable stress of the material. So our factor of safety is below 1, and that is a great cause for concern. You don't want anything running below a factor of safety of 1. This would mean that the material is in fact going to experience a yield, permanent deformation, if not outright breakage. Okay. So how do we correct this problem? Well, now we can go back to the module, to the model, and for example, change the radius of that fillet. And the wider the radius is, the smaller the stress concentration that we should expect. So let's see if we can prove that. So we'll click on here, done viewing results. Let's go back to the model here, find out where this fillet is. We'll see that it's this particular element in here. We'll edit it. It used to be 0.1, so we'll go ahead and make it 0.3, for example. Okay. So 0.3, so we've made the fillet a little bit larger. Okay, we'll click OK there, the part regenerates. We notice that, there's really not a big change to the part. We've just made that fillet a little bit larger, so seemingly an unimportant change. Okay. Now we have the ability to rerun the study. Okay, and this is one of the really, truly beautiful things of having the modeler living in the same sandbox, if you will, as the analysis, as the CAE tool, it's the stress analysis. So we modify the model, or rather set a model, run the analysis, see something that we don't like, go back, modify the model, and then rerun the analysis. So very powerful. So here's the studies being rerun. Okay, so go back to the Simulation Express tab, rerun the model, just as simple as this. Okay, it replaced the animation for us. Okay, we know that it's okay. Yes, continue. Now we could go back and look at the stresses. Unfortunately, I don't recall, what the stress is that we saw before, but we can now plot, our factors of safety. And notice already that our lowest factor of safety has now gone above 1.0. So it went from 0.8 to 1.0. So just making that small modification to the fillet radius, had a very positive effect on the stress level. Now the stress is still, or the maximum stress is still likely to appear in the same place. So in fact, that's what's being indicated by this arrow. In fact, we can visualize it merely by, say, setting the threshold, for the visualization of the factor of safety a little bit above. Okay, so we still see that these are the trouble spots. Okay, but now we know that the stress that's being experienced, according to this simulation, is below the allowable stress for the material. Okay. Now, it would be every bit as easy as changing the fillet radius as to modify the material, as to experiment with a different loading condition, as to experiment with different fixtures, so different ways in which the part would be grounded or fixed in space. So there's a tremendous engineering analysis capability, tremendous insights that you can gain into how different features in your part affect its strength. And this is just at the very, very basic motion, or rather a simulation wizard level. If you go into the high-end simulation tool available through the premium package, you would see that you could do far more sophisticated stress analysis, and of course that would depend upon the nature of the work that you're doing, and just what level of resolution you need with your solutions.